introduce Dr. Diana Davis. She is a faculty member at Phillips Exeter Academy and generally a friend of the Bates Math Department. She's visited us before. And she has with her, I'm maybe even more excited that she has with her some of her students, and they are going to discuss a variety of their projects related to gerrymandering. So I am going to let Dr. Davis introduce her students and get on their way with a series of presentations. So take it away. Thank you.
All right. Thank you so much for the invitation. It's great to be with you, albeit virtually. I hope we can visit you sometime in person. It's such a beautiful evening here in New England. Yes. So last year I was teaching at Swarthmore, and with about 40 students, we did research on gerrymandering last summer. And so Quinn will talk about it, and then Martina, and Corinne, and then me, and then Madeleine. And that's how it'll go. And then at the end, you'll do something. You'll do an activity. So take it away, Quinn.
All right, I will share my screen and then get started. Okay, so like Diana said, we're part of the group of 40 undergrads from Swarthmore that worked with Diana last summer on this project in partnership with MGGG, working on assessing congressional districting, gerrymandering, and graph theory. And then Corinne later will talk about her work doing some graph theory research. But before we get into the math of it, we're going to talk about just the background and the relevant terms that we'll need to get into the weeds of things. So first, at a high level, congressional seats are apportioned every 10 years after the census. So in the House of Representatives, you have your number of representatives for each state based on the population. And then the last census happened in 2020, which is why this is so important now, because as states lose or gain members in the House of Representatives, then the districts have to be redrawn. So in this map on the right, you can see from the last census, the number of representatives that each state had, and you can see the yellow lost representation and the blue gained representation, and then the gray just stayed the same. And the people that are in power in each state redraw the maps, which means that the incumbent politicians can increase chances of re-election by gerrymandering and drawing the districts in different ways. Gerrymandering is the manipulation of boundaries within state or congressional maps for purposes of partisan gain. So looking at the picture on the right, the first picture is just the map of precincts, which is where you vote, which we'll get into in a bit. But you can picture this kind of just as the state. This is our thing that we're going to split up to create districts out of. And just looking at the population, there are 40% Republican and 60% Democrat, but we can draw the lines different ways to make a different number of districts have Republican versus Democrat representation. So doing this, there's packing and cracking, which dilute the voting power of opponents. So the middle picture, the Republicans are cracked, and we can get all 5 of the districts to have Democrat representation versus the last picture, which has the Democrats packed. So most of their voting body is in 2 different districts, and the other 3 are won by Republicans. Because of this, constituents are sometimes misrepresented and the opposition is muted. And there aren't any federal guidelines in place to prevent gerrymandering, which means that states can do what they want. They can have their own laws surrounding it. So gerrymandering takes place at a different level in each state. So then the scales of political geometry, the smallest thing that we have are census blocks. This is the smallest level of geometry, level of geography that you can get basic demographic data for, and the census reports on this. So this is the smallest you can get to protect people's privacy, just the demographics of that, the smallest area, which is not reported on an individual level. And then census block groups are the next biggest, and there's about 39 blocks per census group. And we get more detailed information from the American Community Survey about the demographics here, but since it's more detailed, it's at a higher level. So you get some information, but lose its preciseness. Then precincts are the things that we work with the most as our building blocks. This is your voting, the place that you vote, because everyone that's there has to get the same ballot if there's multiple elections happening at the same time. So everyone at your precinct is the place that you vote. In some places, this is just a city block. In Maine, it's mostly towns. Every town is a precinct. And this is what we'll use as our building blocks for our districts. Then there's counties, which is a smaller geographic area that has its own legislative power. And some states use this as a guide that they don't want to split counties when they're making their districts. Others just completely ignore it. So again, it really depends on the state. And then the biggest thing that we'll look at other than states are the congressional districts. And then each district has one representative in the House. And these are the things that are being gerrymandered to force different representation. So then we talked about that the representation is always fair, but we didn't talk about yet how we can measure whether it's fair or not. So the first thing is looking at partisan symmetry. And this is the principle that a particular vote share received by a party should translate into a specific number of seats regardless of which party received that share of the vote. So in the graph on the right, again, when Democrats receive 60% of the votes, they win 82% of the seats. And when Republicans win 60% of the votes, they also win 82% of the seats. So partisan symmetry is met because it doesn't matter which party gets the 60% of the votes, that party gets 82% of the seats. And the goal of this is to make it go through the 0.5, and it has 180-degree rotational symmetry. And then in the 2016 election, when Donald Trump won despite losing the popular vote, partisan symmetry standard was not met because less than 50% of the popular vote was gained. But since there was only one seat for that, over 50% of the vote of the seat share was gained from the less than 50% of the vote. Another measure of partisan fairness is the efficiency gap, which counts the number of votes that a party wastes in an election to measure whether one party had a systematic advantage in gaining seats through their votes. Any votes cast for a losing candidate are considered wasted, as are any votes for a winning candidate in excess of the number needed to win. So if in a specific district, 40% of the vote is Republican and 60% is Democrat, those 40% are all considered wasted, and the 10% of the 60 above 50% are also considered wasted. This efficiency gap is quantified by convention as total Democrat wasted votes minus the total Republican wasted votes divided by the total number of votes. And it represents which party had an easier time converting their votes into seats. So in this graph, the efficiency gap for many simulated districting plans for the 2014 state Senate election in New Hampshire is plotted, and the slightly negative average efficiency gap means that the Republicans have a more difficult time converting their votes into seats. The ideal is that the efficiency gap is 0 and neither party has a tendency to have more of their votes go to waste. So what I didn't mention is that our group looked at 4 states. We looked at Maine, New Hampshire, Nebraska, and Kansas. So Martina is going to tell you a bit about our experience with Maine.
Hello. So as Quinn mentioned, I'll be talking mostly about Maine and the data wrangling process for it. So essentially, the goal of our data collection was to create shapefiles. And what a shapefile is a bunch of, it's like a map of digital polygons. And these polygons are based off geographic locations, and per polygon, we want to collect a bunch of data. So if you look at the image up here, you see Maine split up into a bunch of small little, what look like almost squares. And as you can see at the top, but in the left bottom corner, it's more abstract, the shapes, I'd say. And you can see that we have a bunch of data to the right, and this is per each of these polygons. We have election data, as in we have like presidential elections and senator elections, how many voted Republican versus Democrat. And then at the bottom, you can also see we have total population, also broken up into racial groups per population per racial group. And we get this data from census blocks, and using this data, it allows us, we can analyze it to see if there's partisan bias. So step one of this data wrangling process is collecting the data. This was fairly easy to do for Maine because the website provided the shapefiles of towns, and as Quinn mentioned before, towns and precincts in Maine had a nearly one-to-one correspondence. And so these polygons I was talking about before in the shapefiles ended up being majority of the towns, which were also the precincts, which was our goal. But another problem Maine ran into specifically was it is quite uninhabited. As you can see, the yellow is uninhabited, which looks like almost nearly half the state. I specifically worked with New Hampshire, and we were also lucky enough to have the majority of the data found right on the New Hampshire Granite website. However, some states were not as lucky. For example, Nebraska here, that team was only able to get a PDF of the data, so they had to convert it manually into a shapefile, and they did this by having to look through an actual map and the roads on the map and trying to line them up to create the shapefile. However, it was not the easiest ride. There were still a few problems faced in the shapefile creation. In Maine, since a lot of areas were uninhabited, the towns got grouped together, and for different elections, different towns ended up being grouped together, which would cause problems with running code because we needed to set a standard per election. We wanted the same polygons being used, but once the standard was set, we were able to reflect the decisions, and problem was pretty much solved. And then another roadblock found specifically for Maine was there was an island inside a lake. Even though this island had 0 reported votes, it still caused a mysterious error for a couple days. But once this was figured out and it was declared adjacent to the nearest precinct, we were good to go again.
Okay, so I will now tell you about the ways that we use, like how we got those histograms of lots of different maps. Okay, here we go. So, oh my goodness, it's like I've never done Zoom before. All right, here we go. Okay, so as Quinn said, the way that people have been measuring whether something is fair is to use these measures of fairness. Like this is the picture that Quinn showed, and you want this to be close to 0. But it turns out that if you have the things that you want, this measure of fairness doesn't necessarily measure the things that you want. So I like to think about it like as asking for a pony for your birthday. You might get a pony, but you have to change your life so much to get the pony that your life wouldn't actually be better. So you could gerrymander your map to get a 0 measure here, but it might not actually achieve the goals that you wanted when you were trying to achieve goals. So that's how people used to do it. But the state-of-the-art method that people are using now is sampling and outlier analysis. So you put some measure of fairness that you like on the x-axis, maybe one of these measures from before, or maybe a measure like how many seats a certain party wins, and then you see whether the current plan is an outlier. So let's dig into that. So here's a proposed way of testing whether a districting plan is fair. You just compute all possible districting plans, and then you measure some measurement, like a measure of fairness for it, and then you measure the enacted one against just the background space of all possible districting plans. So in the upper right is how the United States are cut into its 435 congressional districts. And you might think, let's just cut it up in all the ways, even for a single state. But that turns out to be an intractable problem, even computationally. So if you look at this toy example of the 7x7 grid, you can imagine this as a state, such as Colorado, which is a rectangle that's broken into 49 towns, and you want, or precincts, and you want to make it into 7 districts, each containing 7 precincts. Well, there's 158 million ways to do that. For 9x9, it's 706 trillion, and 10x10 is too big even for a supercomputer. So if you tried to do this with a state, I think Pennsylvania has like 9,000 something precincts, of which it's broken into 421,000 census blocks. It's just a completely intractable problem. And even if you used a supercomputer, it would run until the heat death of the universe before you even were able to measure the fairness of one districting plan. So this is not a good method. So what we do is instead we sample from the space of districting plans. So we're going to use this method called recombination, which comes from the metric geometry and gerrymandering group at Tufts, led by Moon Duchin, who's there on the left. And they developed this algorithm, and they've trained us and other people to use it so that we can assess fairness. So every time we talk about Jerry chain or the resampling algorithm, it's using the computational work of the MGGG. So what it does is it explores the space of districting plans, and you can do this as long as you want. You can get 1,000 districting plans or billions or trillions of plans, depending on how important it is or how long you're willing to wait and how big your problem is. So here's how it does. You take 2 districts, you merge them, you resplit them. Take 2 different districts, merge them, resplit them. So just to go, first you take 2 regions. Let's say here they each have 7 blocks, and you combine them. And then mathematically, here's what's going on. And we'll get into this in much more detail later. You create an adjacency graph, and then you find a spanning tree of that graph. So a tree is a graph that has no loops. And then you find a place that you can cut for equal population. So here, we'll just cut for equal number of blocks, so 7 and 7. And then you split that into 2 regions. And you just do this over and over again. You combine 2 regions, find a spanning tree, cut it, get 2 new regions. Merge 2 regions, find a spanning tree, cut it, get 2 new regions, and so on. And you just do this over and over again until you have gone as much as you want. And this explores the space very quickly. You very quickly sort of forget where you came from. The map doesn't look anything like what it started as. So I'll just do a toy example of how we use this to measure fairness. So imagine a state that's 10 by 10, and it has 40% orange voters. And you're going to, and then 60% pink voters. And you're going to cut it into 10 districts, each containing 10 squares. So this is a time for you to think about what you would accept as fair. How many districts should orange win? Should they win 4 because they have 40% of the votes? Should they win 0 because they don't have a majority? Should it be something in between? Like that's a question that the Supreme Court has considered. They are really stuck on proportionality, but proportionality may not be the right thing to go for. Anyway, you can think about what you think is fair, but here's what our method will tell us. Okay, so here's one way of cutting up the state into 10 districts, each containing 10 squares. And here's another way. So there's 2 ways, and let's measure the fairness of these plans. So here's what we do. We start with plan A. Oh, whoops, I forgot to say something. Okay, we cut it up this way, and you might ask, how many seats does orange win? Well, it doesn't have a majority in any of them, but it wins 5 out of 10 in 3 of them. So you might say on average it wins 1.5 seats. Okay, then in this one, Orange has a majority, that's a 60% majority in 6 of them. So those are definitely safe. And so it wins 6 seats in this one. And you can see that the packing and cracking that Quinn talked about, you can see here pink is packed because it has all of them packed into there. Here pink is cracked because 4, they have a lot, which is 4, but not enough to get a majority. And you can see they're actually cracked in a lot of places and packed in the others. So, okay, so let's see. So we start with plan A. And what we do is we make a histogram. So here's the possible numbers of seats that you could win. And we've marked how many they win. Orange wins on average 1.5, and over here, orange safely wins 6. So we start and we do this merge, split thing, and we see how many seats orange wins. There's the first run, 100,000 different possible districting plans. There's a second one. There's a third one. So those are each 100,000 plans. And what you can see is that one thing is it's pretty stable. Every run is kind of the same. And also 1.5 is in the bell curve. It's not an outlier. It's maybe on the low side, but we wouldn't reject it as being unreasonable. Okay, let's start with plan B. So we merge, split 100,000 times, starting with this plan. So you might think, well, this one is going to have more wins for orange. But look, 100,000 runs, different 100,000 runs, different 100,000 runs. Gosh, it's awfully similar to the previous one. So this makes us happy because we are convinced that this random walk thing very quickly gets lost and forgets where it came from, because these 2 distributions are very similar, even though they started in different places. Since this is a math class, I'll tell you that people have tried to prove that you forget where you came from, mathematically speaking, and it's very hard to prove. But these kind of schematics convince us that it's fine. Okay, so what's the point? The point is 6 is an outlier, like a way outlier. Even if you start with that map, you don't get anything similar. And so here we'd say, okay, that's an outlier. The person who drew this map probably had something in mind other than just dividing the people for representation. So we all were in Pennsylvania, associated with Swarthmore College. A few of us were there, including me, in the fall of 2018, when big stuff happened with this. So let's talk about it. So in the fall of 2018, the Pennsylvania Supreme Court, that is the state Supreme Court in Pennsylvania, threw out their districting plan as unconstitutional. And the Democratic governor enlisted Moon Duchin of Tufts and her team to come up with, to assess whether the proposed replacement plans were fair. So here's Pennsylvania, and it's 9,000-ish precincts. And these are its congressional districts at the time. And Swarthmore is down here in the corner somewhere in a very, just cut out of a very gerrymandered district. It excises Swarthmore so that it can have a tiny Republican majority. But anyway, they started with this plan, and then they did this merge split recombination thing. What happened? And they did it 2 to the 30th times, which is a lot. That's like a billion, I think. Okay. So what happened? So first of all, how about the enacted plan? So this is the plan under which people voted for 9 years, right? From 2011 to 2018. So that was the current plan. And if you started at this plan, then you can see that the whole distribution of plans is like way to the left. So the current plan is a way outlier. This is using the mean median measure of fairness. And then the Republicans proposed a replacement. Now the currently enacted plan was super gerrymandered looking, like it had all these little fractal bits to it. And then the Republicans proposed a replacement, which looked nice and blocky, but actually it had a lot of the same properties. So you can see even if you start with that replacement plan, you get a histogram that makes it a way outlier. And then the Democratic governor, Tom Wolf, proposed a plan. And you can see that his plan was like in the middle, in the distribution, what I like to call the visible part of the distribution. And indeed, it was actually a little on the Republican favoring side. And then if we use this other measure of fairness called efficiency gap, it's a little tougher to understand what's going. This one is not as nice because it's got a bunch of bumps, but you can see that the enacted plan was an outlier in both cases, and the governor's plan was not. So, but another thing we can notice is that if you actually look, I'm not sure if all you can see if you're looking on a big screen or something, but if you look at the x-axis labels, I put an arrow where 0 is. And if you were going for 0 as your like mean median score of 0 or efficiency gap of 0, it's just an unreasonable standard to hold a map to, because it's also a way outlier. And if you wanted to make a map that had a 0 mean median score, you'd also have to gerrymander, and that probably wouldn't achieve like really important goals. So hence outlier analysis, yay. How about Maine? So as Quinn and Martina mentioned, we looked at Maine, New Hampshire, and Kansas and Nebraska. So let's look at Maine. So here's Maine. We've got Lewiston up here somewhere-ish. And so Maine has, as you know, lots of water, like its coastline is equivalent to the rest of the East Coast combined. And so it usually has a bunch of Democratic, liberal-leaning people along the coast, and then more conservative people inland, and then no people at all in the upper half of the state, basically. So what do the congressional districts look like? Well, they look like this. It's a shape that makes a person say, especially, well, one thing is like, I know this picture isn't the best because I tried to overlay 2 maps and they didn't, their projections weren't the same. You know, the Earth is round, not flat. And so when you project the Earth onto a map, you have to make some decisions. And if people don't make the same decisions, then they don't line up exactly. So that's what happened here. Our map projections are different. This is the island of North Haven, and this is Isle Ho. And they are connected to the green, which is kind of funny. And one thing which is interesting is that one of the 2 representatives who was in power when this map was drawn is from North Haven here. And so anyway, that's kind of interesting. So anyway, a person might say, wow, this boundary looks way longer than it should be. And why is there a tail of a whale? That sounds like really on theme for Maine, kind of. Maybe it's a porpoise, but why is it there? A person might wonder. And we are still wondering, and I will have you look at that at the end in the activity. Okay, so here's the same picture as Quinn drew, the efficiency gap for some election in New Hampshire. And you can see that the efficiency gap, if you measure it in the state of New Hampshire, you get this nice histogram, sort of ish, centered around 0. And the enacted plan was like, definitely in the middle. I mean, that's definitely in the middle. So we didn't find that New Hampshire was gerrymandered based on this measure. You might say, why aren't you showing me a picture of Maine? That's a great question. Again, for New Hampshire, another way we could do it, what this picture is these are the 2 districts. These are the measure of how many Democrats were in each, what the Democratic percentage was in each of the simulated districts for 100,000 runs. And you can see that the enacted plan was like, it's like right in the middle of this box and whisker plot, basically. This is good. I mean, you might say, oh, this one's a little above, this one's a little below, but like, that's really close. I have seen this for Utah, and the enacted plan was like way at the bottom and then way at the top, which indicates packing and cracking. This one is nice. So no problems. New Hampshire seems good. But how about Maine? So here's the thing about Maine. Well, if you look at the Senate, so for a lot of the elections, you'll see that both districts, the least Democratic district and the most Democratic district, are both voting Democrat. So there's this 50% line, and that's cool. And that happens for most of them. But then the Senate elections are super different. So they go way Republican, which is because Susan Collins is a very popular senator in Maine and has been the senator of Maine since before everyone present in this space was born, except for the 3 professors. She has been reelected since like a really long time. So anyway, so the deal is, here's the deal. All these wonderful measures of fairness really only work if you have different parties winning in different districts. So for New Hampshire, because New Hampshire is razor thinly close to 50% on everything all the time, we could get a lot of elections where a Democrat won one district and the Republican won the other. But for Maine, it wasn't that way. So our data looked bad. Here's an example of something like for New Hampshire, we would get histograms that look like this. And in Maine, it would just be the entire bar would be at the 50%, because 50% of votes are always wasted. in every election. And if the Republicans always win, they're always Democratic votes. That's how it is. No, that's not true. Anyway, it's always 50%. It's hard to figure out on the fly, but it's always 50% if the same party wins both, because you have over 50% wasted always. Okay, so Corinne is going to talk about some pure math questions. You might ask, like, what if the tree splitting goes wrong? Like, what if you merge these two districts? You create an adjacency graph, you find a spanning tree, you try to cut it for equal population and you can't do it. Well, then I guess your algorithm would just stop right there and give up. That would be sad. Corinne has been working on something like this. And what if you merge two regions and then you try to resplit in a different way? But check this out. If you're going to resplit, these 7 always have to be together. And so if you resplit, you'll just get the same thing back. And so this kind of thing, that's just a tiny taste of the fact that this very applied problem in trying to solve like a social justice problem creates really interesting pure math problems. And so even if you just like doing pure math, you can solve these problems about pure math, and then they'll feed right back in and help to improve the algorithms and advance social justice, which is our goal.
Okay, so I worked on problems when you're trying to split trees that are trees of or spanning trees of adjacency graphs, that every node has a different population, because in the real world, when you have a map of some place and you're splitting for equal population, not every precinct will have the same number of people. So Jerry chain, this is very similar to what I said before, but Jerry chain makes new districting plans from old districting plans in this tree splitting method. And so the goal is to create new districts that have approximately equal population, and approximately is defined by however different you want them to be, or are willing to accept them to be. So you select 2 adjacent districts and merge them into a single district. And then you draw a uniformly random spanning tree, and then removing any edge of this tree will break the tree into 2 components that are both connected. And so then you get 2 connected districts. And the goal is to find an edge of the tree that breaks the tree into 2 components that have approximately equal population. So you're not just looking for equal number of blocks in each component of the tree, but you're looking for equal populations. And so this edge would be called a balance edge. And if 2 components of a spanning tree have with the balance edge removed, becomes the 2 new districts in your districting plan. So for instance, this spanning tree has a balance edge, and when you cut it, you get 2 new districts, and the populations are 14 and 15. So that's approximately equal. If you're willing to find 14 and 15 as approximately equal. And so in order to do this, Jerry chain randomly selects edges of the tree and checks if they are balance edges. So it just selects an edge and then looks at the components of the tree when you remove that edge and sums up the population. And if they're the same, then you're good, but there's a lot of edges in a given tree that are not balance edges. So if it doesn't find one, what happens? So the problem is that some trees don't even have balance edges. You can draw a spanning tree at random and it might not have any edge that you can remove to break it into 2 equal components. So when Jerry chain is looking for such an edge, it's just choosing edges from a tree that doesn't have a balance edge. To solve this problem, Jerry chain basically just says, if I don't find a balance edge after checking like some number of edges, then I'll just stop and then redraw a spanning tree and then start checking in that tree. And a question that I was interested in is there a more efficient way to determine if a tree doesn't have a balance edge, And can I find one more efficiently than just checking at random? So for instance, here's just like a very small tree that has a total weight of 12. So every node is weighted with some population. And removing this vertex, and you might be interested if this tree has a balanced edge, you might quickly determine that it doesn't. But one property that this tree also has is that when you remove the vertex V shown in red, it gives a forest with 5 components, and none of these components have approximately half the population or half the total weight. So you can define a balance edge more precisely by saying, let T be a vertex weighted tree with total weight of S, and an edge is a balance edge of the tree if the components, when you remove the edge, have weight within some specified range. So S/2 plus or minus some population deviation. And so if the tree contains this is a different way to look at it is if a tree contains a vertex such that every component of the tree with the vertex removed has a total weight less than the minimum that you're willing to accept, then the tree doesn't have a balance edge. And this is another way of looking at balance edges that gets you there a little bit faster. And so the reason why this is true is that if you remove a vertex V and the tree does have a balance edge, then either it's the vertex, it's incident with the vertex that you removed, or it's in one of the components that you get when you remove a vertex from a tree. And so suppose that the tree contains a vertex such that every component has weight less than the minimum that you're willing to accept for population. And then also suppose that the balance edge in fact contains an edge, a balance edge. So the first case is if the balance edge is incident with the vertex that you removed, then one of the components has to be the component that the edge connects the vertex to has to be within the population range because it's a balance edge, and therefore when you remove it, you will get that component as one of your components. So this is a contradiction. And then the second case is if the edge is contained in one of the components, but every component has total weight less than the minimum that you're willing to accept. So removing any edge out of that will just create 2 smaller components, which is not possible. So the balance edge cannot be in that component. So this gives another algorithm for finding balance edges. Is you basically you start from a vertex and you're looking for a vertex that when you remove it, either you get a component that has total population with what you're interested in, or every component has total population that's less than whatever range you're willing to accept. So then you can stop looking. And so to find this, you start by choosing a vertex that has maximum degree and maximum weight. And what this does is it minimizes the total weight of the tree when you remove this vertex, and it maximizes the number of components. So the average weight of every component is minimized. So you'll look for this vertex and then you'll remove it, and then you'll look at the components. And if there's a component that has total weight with a population that you're willing to accept, then you can just take that component and you take the balance edge to be the edge that connected that component to the vertex you removed. And if it is above that, above the maximum that you're willing to accept, which it often can be, then you step in the direction of the heaviest component or the most weight, most populous component. And then if every component has less than the minimum population that you're willing to accept, you can, you know that this tree doesn't have a balance edge, so you can just draw a new spanning tree. And once you step in the direction of so if you have a component that has total population that's above what you're willing to accept as approximately equal, then you step in the direction and remove the vertex that was in that component that was adjacent to the vertex that you initially removed, and repeat the process. So to see this in a graph that is much bigger, I've made a graph that has a bunch of nodes, and the size of the node indicates how much population they are. And so we start by looking for a node that has maximum population and maximum degree. So the maximum number of other nodes that it's attached to, which is this vertex shown in red. And so then we dissolve this vertex and we get a bunch of components, and they all have different population. And this blue component that's still blue is definitely the biggest one, and it's definitely not about half of the graph. So then we go in the direction of this component, and we remove the vertex that the vertex we initially removed was adjacent to, and then we repeat the process with this component just being our graph. So when we remove this, we get two components, and then one of them is definitely not half of our graph. Two of them are definitely not half the graph, but the other one might be. And so we step in that direction, and maybe it's a little bit over. So we need to take a few more vertices from this side of the tree. And so then we remove it again, and maybe the blue component is exactly approximately equal. And so then we know that the edge connecting that component to the vertex we just removed is the balance edge. And so then we have a balance edge, and then we're happy. And that's it.
Right, so we dug in super deeply to, so Corinne dug super deeply into the data, and Martina said how to get it, and I said some of the guts behind it, and now Madeleine will show how we use this to advance social justice.
All right, hi everyone. I'm going to be presenting on prison gerrymandering, which I worked with the group on this summer, and then I also returned to it for one of my senior projects in the fall. And so this is an application of some of the math and algorithms that everyone's been discussing so far. That's a little bit taking it in a different direction. So just as a piece of background, prison gerrymandering is a little bit more unintentional than typical gerrymandering. It's not decided by a party in power, but just by the practices that already exist. It's the practice of the census counting incarcerated individuals who live in prisons as residents in the district of their correctional facility, or in the census block of their correctional facility, rather than their actual home. This might not seem like a super big problem, but it actually is that this is the type of counting that's the default, although there are some exceptions, which I'll get into, because around 1.3 million people are incarcerated in state and federal prisons in the United States right now. That number has been going up and down, but it's a huge amount. And so just thinking about it practically, we're saying that the majority of those people are probably being counted in places where they don't actually live. And so one of the main implications of that is based on the disparities between who goes to prison, where they're from, and then where the prisons are located. So in many states, and in states, especially with large incarcerated populations, the prisons themselves are located in really rural areas where they just have more space and it's cheaper. And so it's not unusual that the biggest prisons can be found in those rural areas. However, it makes common sense that urban centers with large population densities are the ones that see most of their residents going to prison. And this is not even to mention the racial disparities in who gets disenfranchised and imprisoned. Prison gerrymandering is a form of systemic racism because it disproportionately dilutes the political power of Black and Hispanic people. So it's essentially double counting then this disenfranchisement, because in most states, prisoners cannot vote, but because of prison gerrymandering, as also in most states, prisoners do not even count towards the political clout of where they're supposed to be from. So to get into an example of the effects of prison gerrymandering at the precinct level, which we mentioned was just the voting level, consider two precincts, one in a rural area A and then one in an urban area B. These are based on real precincts in Pennsylvania, which I'll get into. So in precinct A, which is in a rural area, the population of the precinct is 2,000, but there's a large prison there with a population of 3,500. There are 9,000 total precincts, or somewhere around there in Pennsylvania. So consider that with these small populations expanded. There's a lot more prisons than just in precinct A. But okay, so the census occurs in 2010, and the census counts the population of precinct A to be 5,500. So more than half of those people are not actually living in precinct A. And this is true for most prisons in those rural areas, because prisons, unlike jails, are not composed of people who live nearby for the most part. You could live in Philly and then go to a prison somewhere in the middle of the state, and that's not uncommon. So let's say urban precinct B is located in Philadelphia, the biggest urban center in Pennsylvania. It has a population of just over 5,500, but 25 of those, we'll say, are population that is incarcerated, and they are located in prisons elsewhere. There are no prisons long-term in Philadelphia County. And so the census too counts the population of the urban precinct B as 5,500. So according to the census, precincts A and B have the same population. But voters in precinct A have almost 3 times the political clout that voters have in precinct B. And so their vote counts for more. Just as a reminder, legislative districts, of which Pennsylvania has 203, where each district sends representatives to the state government of Pennsylvania, are also made up of precincts. So we know that the congressional districts, of which Pennsylvania, I want to say, has around 5 or 8 or something like that, they are also composed of precincts. Same for the legislative districts. And so that's what I'll be talking about in these examples that I'll be giving. And so the district then that has precinct A, along with hundreds of other precincts, is inflated in power with thousands of non-voting population. Because again, in Pennsylvania, that's one of the states where prisoners cannot vote at home or where they are located. So, and then think then again about the density of an urban precinct B and the precincts around it in such a densely populated area as Philadelphia. It's not crazy to assume that other precincts nearby precinct B will have similar situations. And so those 25 per precinct really start to add up. And then the districts that contain all of those precincts are losing political power. And so, like I said, this effect is amplified in states where prisoners do not retain the right to vote when they are incarcerated long-term, because now they are unwittingly contributing to the political power of the area in which they are incarcerated without even being able to officially hold civic ties to that area by means of voting. Okay, and so there's a couple ways that states can end prison gerrymandering. Like I said, it's a problem with the census counts. And so it is the default because the census is just the one organization and is national. But states can pass laws that outlaw prison gerrymandering when constructing districts. So just as a reminder, districts then are redrawn every year after the census. So in 2021, 2031 will be the next time. 10 states have outlawed prison gerrymandering for the 2021 redistricting cycle, and 4 states have bills in progress to do so. By far the most comprehensive solution is to pass a federal law. There's actually one in the Senate right now. It's called For the People Act, but this would not take effect until 2030, and it's not even a sure thing because people do not like prison reform, and there's also a lot of other things like enfranchisement that are included in that bill, but I urge everyone to read it. It's very interesting. There's also a lot of local ordinances where local governments can revise the census counts before redistricting. This is not perfect because in most cases, they are not counting incarcerated people in the districts where their prison is, but they're also not counting them in precinct B or wherever they're from. So, so they're just not counting them at all. So they're still losing political power, even though we're not seeing the huge inflations that would be in precinct A, like I mentioned earlier. Okay, so to briefly look at Maine, it is not one of the states with laws outlawing prison gerrymandering. It has a relatively small prison population and prison rate. This is below the national average. And in Maine, Vermont, DC, and Puerto Rico, incarcerated people can vote, but have to do so by absentee ballot. So in this case, in Maine, people who are incarcerated are able to vote in their home district or their home precinct, but they're not counted towards any political power that that precinct has in actual elections. So yeah, like I said, Maine has not outlawed prison gerrymandering for 2020 census redistricting. My group this summer looked at Pennsylvania, which is a state that has one of the highest rates of incarceration and has over 42,000 people in state prison alone as of recent data. Of those 40, more than 40K, more than 25% of them are from Philadelphia County. So Pennsylvania has 67 counties. For just some perspective, Philadelphia County is huge and has a really high population density. So it contributes to more than a quarter of those state prisoners. Moreover, 47% of those more than 40,000 are Black, despite only 10% of the population of Pennsylvania being Black. Many of those people are from Philadelphia, which has a really high Black population. But in any case, the rate of Black imprisonment in Pennsylvania is more than 4 times the general rate of imprisonment. So because of this really big difference that we're seeing, and then the political makeup of the state, Pennsylvania is purple. And not only that, but in most of the urban centers and in Philadelphia, the political leaning is really, really blue. Whereas in rural areas, it's very, very red. And so because Pennsylvania is also not outlawed prison gerrymandering, my group suspected when we began our project that there was a partisan skew that was occurring as a result of all of these prisons in those rural areas that was maybe giving more political clout to areas that are leaning Republican. So that was something that we sought to address in our research. We already know from previous research that prison gerrymandering in Pennsylvania, because of the just huge quantity of incarcerated people, distorts district sizes. And so again, these are legislative districts. There are 203 in Pennsylvania. And so these rural districts that contain prisons seem larger when incarcerated people are counted there. So this graph that I have here is from a study that showed that if you eliminated prison gerrymandering and in theory returned all of the people who are in prison to be counted in their home precinct or home census block, then 8 districts would be either legally too large or legally too small to comply with guidelines about district size that are in place. And so that's one issue with prison gerrymandering, is that it would require a big change in the shapes of the districts if it were to be revoked in Pennsylvania or outlawed. And so those 3 pluses that you see there at the bottom are for Philadelphia. Like I said, that's where the vast majority of incarcerated people come from. So you would expect that if prison gerrymandering was outlawed, Philadelphia County and the region surrounding it would get a lot more political power, which we suspected. So we wanted to know whether prison gerrymandering being outlawed would also change which parties will win state elections because of the political power of the rural counties leaning more Republican. And so we suspected that maybe it would go a little bit more blue if prison gerrymandering were to end. Okay, so turns out it is not very easy to get data from state agencies. We required for this project knowing the number of people who were incarcerated, which was pretty easy to find out, but we also wanted to know where they came from so that we could reallocate them, which is a word I'll be using a lot, back to where they were originally from, so that we could compare legislative results and voting results for unadjusted population with prison gerrymandering in effect, and population after adjusting for those returns back home. So we knew each of the precincts that the prisons were in, but the state only provides counties for the location of the incarcerated people. And you'll notice that it's committing county. So it's the county in which the person committed the crime. This is the best proxy we have for county of origin. So warning, there's a lot of error incoming in these analyses just because there's certain restrictions about what you can know as a citizen. So I should mention that we want precinct information, and I'll get more into how we got this, but we wanted precinct information because we know that both counties and legislative districts, like I said, are both composed of precincts. So it's the smallest or the largest geography that those two share as a component. And so in order to get from county to district, we'd have to go through back down to precinct. And so it was of relevance to us to know which precinct the prisons were located in, which we do know. So we could subtract from those precincts, and then also the precinct where the incarcerated people came from, which we did not know. So we wanted the county level data because that's the best we had. This was an enormous pain to get. This is the database that you're looking at right now, the database that Pennsylvania has for public access. It's very restricted. You can only see a certain number of results at a time. Pennsylvania has something called the right to know law, where you can get this information in an Excel spreadsheet for all people imprisoned in state prisons, which was relevant to us. And that's over the 40K that I was mentioning earlier. The data request takes up to a month to fill, and of course they took that whole month. But we only had a summer, so one of my main tasks this summer was to actually scrape what I could from this database. And of course it's limited because of course the state doesn't want people to do that, but imputed the rest. And then when we received the full data a month later, luckily all of the analyses were already set up so that we could just correct the small corrections that we'd have to make. And it was not too different from what we expected it to be. Another problem was the data. And so I'm going to talk now about how we address the fact about having county information or a proxy for county information, committing county, and wanting precinct information. So we had to take a step in our reallocation process, like I said, called spatial disaggregation, where we are disaggregating the total count for each county, of which there are 67, to the total count being returned to each precinct. And so that was the next step in the data analysis here. Spatial disaggregation, like I said, goes back from counts at the county level to counts at the precinct level. So the map that I'm showing here is the number of people returned to each of the 67 counties in Pennsylvania. I say returned, we're just envisioning this to be some sort of dynamic process where all of the people who are currently located in prisons are floating back to wherever they lived originally. And so the really dark blue is Philadelphia County. So I'll be focusing on that just to give you a close-up of those precincts. One of the main ways to do spatial disaggregation, there's a bunch of different ways, but probably the most relevant for us was using some form of population weighting based on the common sense that places with a higher population density probably see more people going to prison. And not only that, but for Philadelphia County, it turns out that at the county level, the number of people in each county, population-wise, and the number of people going to prison were highly correlated. So we could confirm that. And then, so one of the first steps that we did, or might do, is use simple population weights. So these are all the precincts in Philadelphia County. And so I have up to 100, it looks like up to 100 people returning to each of the precincts. The distinguish is not super large, sorry for the scale, but so this is an analog to the map on the left, where we have the number of people returned to each of those precincts. This would be using simple population weights. As it turns out, there's more than just population related to imprisonment. In fact, you might suspect that racial makeup of that county was also highly correlated with the number of people from that county who go to prison. So for example, highly white rural counties probably don't see a lot of Black people going to prison there, and vice versa. And so it was probably great to reduce error as much as we could. So for our analyses this summer, we used racial weights as well as population weights. This was also something that I worked on during my project, as I mentioned in the fall, as part of my senior project, in finding the absolute best way to minimize the error in this process. Because as you can imagine, we're going from 67 counties to more than 9,200 at that time precincts in Pennsylvania. There's going to be a lot of problems with any weighting mechanism that you have. But this is the most sophisticated mechanism that I ended up with, which was using weights based on racial data, education data, and of course, just general population. So darker colors mean that more people were added to each of those areas. They're not exactly split into precincts because this was a different method, like I said, than the simple population weights. And then you can confirm then after that, that it is highly related to some of the racial weights that we were using. Race is very relevant. And so I just put up this graph on the right-hand side just to show the percentage of the Philadelphia County population that identifies as Black by census tract, which lines up roughly with the amount of prisoners returning. And that's just because Philadelphia has such a high proportion of its residents who identify as Black, and also because most of the people who go to prison, or a huge plurality of those people, are Black in Pennsylvania. And so that ended up being highly relevant information. So like I said, there's a huge amount of uncertainty here, but this was the best that we ended up with. And I will remind you that we only knew committing county in the first place. So we can't even say that this is exactly where they came from. The state has that information. They do not give it out publicly, but that's all right. So we could get something from this, which was the total number of people to return to each of these precincts. So we imagined that we had those 9,200 precincts in in Pennsylvania, and that we were returning people and taking people out of precincts that had prison populations and then moving them and dispersing them throughout the state. So this graph shows how the precinct populations change of those 9,200 precincts when those people are quote unquote returned. Obviously they are not physically returned, but that's the metaphor I'm going with. So you might suspect that those orange and red precincts are areas where the prisons are, and you'd be correct. But you see that although there's a huge amount returning to Philadelphia, where I've zoomed in on, and also Allegheny Country, which is over on the left-hand side in that other urban center, that's just an enormous amount of people. But the people are returning to everywhere in the state. And so, of course, there are also people who are incarcerated in the same county where they committed their crime. That was more unusual than most, but there were people returned to every precinct in various weighting amounts. And so the total number of people returned within each of those precincts within a given county did add up to the amount that we knew were from that county. And so, yeah, so we finally had these results. We had the number of people added and subtracted from each precinct. And so we would add that to the total population, and this was all 2010 data. So this was the total 2010 population of each precinct, which we also had. And we would end up with an adjusted population. So then finally we could run the recon method and run the algorithm. And there's a couple things here that are important. So this is an example for using state attorney general vote for Republicans and then Democrats. These are just mirror images of each other. So if you only want to look at one of these graphs, that's also fine. And so the idea was to get a sense of how each of these 203 legislative districts would vote, either Republican or Democrat, if they were given an election like Attorney General that is really partisan and not really related to personality or any other factors. And so that's why we would use the Attorney General race. And so this was 2016 data as well. And so you'll see that unadjusted population over here on the Republican side, I'm showing it as the light orange. And so that would be before we ended prison gerrymandering, hypothetically. And so this little green area that I've outlined is the total histogram of Republican wins before we ended prison gerrymandering single-handedly. And so the adjusted in the other case would be exactly the opposite. So we're counting the Republican wins out of those 203 seats. And so you see that there's less out of those 203. And so the mean's somewhere around 114 after we've adjusted. And it was somewhere around 117, 118 before we adjusted. And so this process for us seemed to suggest that there is a partisan skew in Pennsylvania. If there wasn't, we would expect that these histograms would overlap entirely. They do overlap somewhat, but the means are definitely different. And then if we ended prison gerrymandering, according to a graph like this, Democrats would win between 3 to 6 more of the 203 total districts if prison gerrymandering were to be as easy as just getting rid of it. There's a couple of caveats to this conclusion that I do want to mention. Firstly, we did not run many occurrences. So you might remember from previous presentations that 100,000 is somewhat of a gold standard. These histograms are really choppy because we only ran 1,000 different recom iterations. And so you would get a lot smoother graphs and a lot more certainty if you ran more occurrences. The second thing, which is kind of big, is that states prefer to maintain county boundaries when assigning legislative districts. And so we did not ultimately get that code to work to maintain county boundaries. So that's not a restriction that was in any of this recombination work that my group was able to do. And so some of these boundaries might be impossible, or some of the, for example, some of the outliers on the scale might be impossible if we were to maintain the county boundaries in the districting. But this is really promising. And I think the next step then for people in my team or me would be to use the 2020 census data, which will be coming out or maybe already has, to update a lot of these counts. This, like I said, was all 2010 data. Pennsylvania has not taken any action to end prison gerrymandering since then. So maybe next time. But like Diana was saying, there was a lot that they were already committing to for regular gerrymandering. But really the best way is with some sort of federal law or federal correction to the census counts that doesn't put the burden on the states. Because like I said earlier, this is not really an intentional move by parties. It's just how the census counts things, and it would take some adjusting to fix that issue. But that concludes the work that my team did. Thank you so much for listening. If you're interested in doing this for Maine, we didn't see anyone do this for Maine yet. So maybe that's something that anybody wants to work on. But yeah, this does not get as much attention as it should, but things are being done at a glacial pace. But hopefully this is interesting.
All right, so we'll do an activity later, but that concludes our presentation for now. So thanks.
Thank you so much. I hope you heard our applause. So Dr. Davis is really generous and willing to stick around tonight to lead us through an activity where you're all going to get to develop some of your own districts. So I'm going to let her explain it. We're going to need the Zoom folks will be in a breakout as one group, and then in the room we're going to split you in half so that we'll have a total of 3 groups. So let me hand it over to Diana to explain, and then we'll work on logistics.
All right, so as we explained over the summer, we gathered data and we made these shape files. And one reason to make the shape file is so that we can assess whether things are fair. But another reason is to empower people to make maps. So for instance, people have said in the past things like, oh, it's not possible. So Pennsylvania has 18 congressional districts. It's not possible to make 2 majority Black congressional districts in Pennsylvania. And it is hard But if you have the tools like computational tools and you have like 1,000 people, or let's say 24 in this room working on it, you can do things. And so we collected data so that to empower people to do things. So here's the thing. I'm going to show you how to use this website called districter.org, where our data went. So it went to districter.org and it also went to GitHub. So there's districter.org, and I'm going to share my screen and show you how it works, and then send you off to do it yourself. So districter.org has a lot of explanation on it, but you can click here, jump to the map. And then of course we want to redistrict Maine because it's our favorite. So I'll click on Maine. And there's things you can do. Let's build 2 congressional districts built out of precincts. All right, so it loads up Maine here. And then just one thing is it just shows a lot of data. So the first thing I'll do is show you the data layers. So here in the data layers, you can show the tribes, where they are. You can show population, where do the people live? So it colors it based on population. You can kind of see where people live. And you can also show partisan lean. So for the purpose of this exercise, so we collected data for 6 different elections and attached it to the shapefile. Since we're doing congressional districts, let's do a House election, and let's do the one that is earliest, so 2016. And then if you click show partisan lean, it'll show you how is the partisan lean of each of these little precincts. And you should take some of these really dark ones with a grain of salt, because there's probably like 3 people there and 2 of them voted Republican. But in the populated areas, you really see what the makeup of the state is. And then if you want to know about things, you can take this magnifying glass tool and hold it. Oh, there's 3 people there. Yeah. No, wait. Oh, that's how many precincts. Oh, I see. That's how many people. So there's 0 Democrats and 2 Republicans in that precinct there. So that's why it's so dark. And Lewiston is in here somewhere. But you can see sort of how it is if you hover over the correct one, and you can zoom in, which I'm not going to do, but you can. So let's do this. So here's what we can do. So I want to make 2 congressional districts. So so here's how you do it. You take this paintbrush, let's make it extra super big, and I'm going to just paint. And so as you can see on the right, my population is going up. I've got that much of Maine, and I only have 84,000 people. So here I go, making my congressional district. I like Deer Isle. I've got Deer Isle on it and a bunch of other stuff. And soon I'll have enough. And there we have it. Okay, great. Now I'm going to make the other one. I'm going to lock already drawn districts so I don't paint over myself, and just paint the rest yellow. And so those are my 2 proposed congressional districts. That is a gorgeous districting plan if I've ever seen it. And my population deviation, you can see here is 1.66%. That's pretty good. But if I wanted to, I could fix it by what? Making a few more blue. Maybe I'll make my brush smaller. Nope, I want a few more yellow. And gather a few more until I get, oh, that's not working because I didn't unlock. Get a few more till I get like a really great population deviation. Okay, that's pretty good. So my 2 districts have the same population. Cool. Now what we want to know is, suppose this was the enacted districting plan in Maine, how would it shake out? One thing you can do is like look at the racial makeup of it. Honestly, for Maine, this racial makeup is not too interesting. It's pretty consistent across the state, 95% white. But you can look at something like partisan balance. And you can see that for the US Senate election in 2018, everybody voted for Susan Collins. So this is not a very interesting election. Let's change it to the 2016 US House election, which is the colors that I put on the map. Oh, here you can see that in District 1, the Republicans won, and in District 2, the Democrats won. And then if I want, I can go change my districts to make something else happen. So there's the situation. And what else? You could change to different elections and see what would happen with your districts. But if you would, let's all use the same election, and let's use the 2016 US House election, just because. So there we have it. Okay, so your quest, should you choose to accept it, you will be in 3 groups. So one group will be Group Democrat. So Group Democrat, your charge is to create 2 districts so the Democrats win both districts in the 2016 US House election. So that was about a 51.5% Democrat, 48.5% Republican election. So in theory, You could get Democrats to win both if you made them carefully. Let's do it. How about group Republican? So the Republicans are winning 48% of the vote, which is almost half. So it would be nice if the Republicans could safely win one district. So try to make 2 districts so that Republicans safely win one. Safely means it has the highest possible Republican percentage that you can. You don't want to have just like 50.1%, because then what if a couple of people get a cold and they can't vote? You have a problem. You want it to be as safe as possible. So that's a Republican group. And then the third group will be the incumbent group. So we didn't talk about incumbent gerrymandering, but incumbent gerrymandering is gerrymandering so that the people in power will get reelected. So in this case, there were 2 Democrats who were in the House of Representatives when these maps were redrawn. Let's see, one of them lived in Millinocket, which is, let's see, oh yes, I brought this up on the map so you could see it. Here it is. So one of the people lives in Millinocket, and the other person lives on the island of North Haven. And so this is roughly, well, this is exactly where they are. You can be rough on the map, but that's North Haven. And so you want Democrats to win 2 different districts, and you want these people to be in different districts, because of course, if you put them both in the same district, they'd have to compete with each other and one of them would lose, and they don't want that. They want to keep their job. That's what politicians want. So group incumbent, please gerrymander for Democrats to win both, and in particular, people of power to be able to keep staying in power. That's your job. Ready? Go.